Hello everyone. In today's session we'll learn about Thevenin's theorem. Thevenin's theorem is very important in circuit analysis. It is mainly used to simplify circuit and determine a voltage or a current across a component for different values. In this case, or in this, when we apply Thevenin's theorem, a large circuit or a complex circuit can be replaced by a single independent voltage source and a single resistor. This is very important to simplify the circuit, and as I said earlier, to determine a voltage or current across a given device or element for different voltage and current values. So, for instance, let's say we have a network of maybe hundreds of resistors and multiple voltage and current sources. And again, we have a load. And then our goal is to characterize the power consumption or the voltage across this load for different voltage values given in the complex network. So what we do is first we'll transform or we'll simplify this network into one voltage source and one resistor, nothing else. So the whole complex circuit is replaced by one independent voltage source and one resistor. Now that independent voltage source, so this voltage source is the Thevenin voltage, or the open circuit voltage between A and B, and this resistor or RTH is the Thevenin equivalent resistance of the network across terminal A and B. So once we calculate VTH, or the Thevenin equivalent voltage, and the Thevenin equivalent resistance of the circuit, then everything is replaced with these two. Then it's easier to work with these two components to determine the voltage and the current through the load and the voltage across this load resistance or this component. When we look at it in terms of these parameters, we can say that these two circuits, let's say this is figure 1 for the first circuit and figure 2. These two circuits are equivalent in this case. They're equivalent. So that means this I, current that passes, or the current that flows through the load, is exactly the same as this I. So we get the same current, whether you use the first network or the second network. So VTH is nothing but the Thevenin equivalent voltage or the open circuit voltage at the load terminals. So this is A and this is B. So VTH is the open circuit voltage between A and B. And RTH is the equivalent resistance of the circuit, again, between these terminals, between A and B. RTH is the equivalent resistance of the circuit between A and B when all the independent sources are turned off. So when we determine the equivalent resistance, make sure to remove all the independent sources. If we have independent voltage source and independent current source, we have to remove. Remove means replace the voltage source by a short circuit and replace the current source by an open circuit. By doing so, we can calculate or determine the equivalent resistance of the network. So these are the two things we need for the Thevenin equivalent circuit. So in order to find, so this is the Thevenin equivalent circuit of equivalent. So this is the Thevenin equivalent of that network. As I said, it is replaced by a single independent voltage source and a single resistor. So what we did is we replaced everything by a single voltage source and single resistor. So this is the Thevenin equivalent circuit of this network. So to determine those two things, the volt VTH and RTH, for VTH, we have to leave the terminal open and solve for VAB. And for RTH, we have to remove all the independent sources and replace that, replace the voltage source by a short circuit and open circuit by an open circuit, and then solve for RTH. Once we determine the Thevenin equivalent circuit, then it's easier to determine the current through the load, or IN. We can easily determine that. Now this is, as I said, this is the Thevenin equivalent This is a Thevenin equivalent circuit. If you are asked to determine the Thevenin equivalent circuit, you are asked to determine VTH and RTH. So the first step is draw this circuit and then solve for VTH and RTH. Once you determine the Thevenin equivalent circuit, as I said, it is easier to determine for IL. And how do we determine that IL? For instance, let's apply KVL through this loop. If you apply KVL, becomes minus VTH plus IL times RTH plus IL times RL equal to 0. And if you rearrange this, you'll get VTH is equal to IL times RTH plus RL. And then this will give you that. That's how we determine this expression. So this expression is used to determine the current through the load resistance RL. So we just used a simple KVL, and using that KVL, we get this expression. Now, if you know IL, which is the current through the load resistor, then you can easily determine again VL, or the voltage across the load resistance. VL is this one, plus minus VL, which is the voltage across this load resistor. So if I want to determine that, I use Ohm's law, V equal to I times R. Now this is VL, the voltage across the load resistance. So IL is the current through the load resistance, and RL is the load resistance. I have IL and RL, then I can multiply these two and determine VL. That is the same as, this is the expression for IL. If we plug here, you will get this expression. And if you see this is nothing but a voltage division rule. It's a voltage division rule. So since RTH and RL are connected in series, we can also use a voltage division rule to determine the voltage across the load resistor without using the current IL. So if you know IL, it's easy, you can use Ohm's law, but if you don't know the value of IL, then you can still use voltage division rule to determine VL. But in both cases, to solve IL and to solve VL, still we need a Thevenin equivalent circuit. We need a Thevenin equivalent circuit. That means we need to determine VTH and RTH. Okay, so this is about Thevenin equivalent circuit. So in Thevenin equivalent circuit, complex circuit can be replaced by one voltage source and one resistor. And this voltage source and this resistor are connected in series, as you see here. We have another approach, which is Norton theorem. Now in Norton theorem, or in this approach, what we do is any linear circuit or a network, two-port or two-terminal network, can be replaced by one independent current source. Here we have current source. So one independent current source and a resistance. So that is Norton theorem. So any linear two-port circuit or network can be replaced by an equivalent circuit consisting of a current source IN in parallel with a resistor R. Now in this case we put N to show that that is a Norton, the current for the Norton equivalent circuit. So, and R is the equivalent resistance, and again we put Rn to show that that's a Norton equivalent circuit. For Thevenin, we just put TH to show that that is a Thevenin equivalent circuit. But for Norton, we put NN to show that that is a Norton equivalent circuit. Now, IN is the short circuit current between terminal A and B. So this is IN. How do we determine IN? We'll short circuit the terminal, this A and B, and determine that. So that is IN. So we short circuit that and solve for that short circuit current. So that is the Norton current, or the short circuit current through these terminals. But for Rn, we use the same approach. For Rn, we remove all the independent sources. That means if we have a voltage source, we'll replace that with short circuit. If we have a current source, we'll replace that with an open circuit. Then after that, we determine the equivalent resistance of the network. So let me erase this. So for Rn, we leave this open, and we remove all the source in the circuit. And after that, we determine the equivalent resistance, which is going to be the Norton equivalent resistance of the circuit. So that's one way. The other way of solving for the Norton equivalent circuit is first determine the Thevenin equivalent circuit and then use source transformation. Because we say that a Thevenin equivalent circuit has one voltage source plus minus, let's say this is VTH, and one resistor, which is RTH. And let's say this is a load resistance RL. And this is a Thevenin equivalent resistance. And the Norton equivalent resistance, we said we have IN, which is the Norton's current, and Rn, the Norton equivalent circuit, equivalent resistance, and the load resistance between A and B, which is RL. So this is the equivalent, the Thevenin equivalent circuit between terminal A and B. This is again the Norton equivalent circuit between terminal A and B. So the Thevenin and Norton equivalent circuits are related by source transformation. And it's very easy to see that, right? So you can see that the voltage source, the voltage is connected in series with the resistor, or the resistance RTH, and that can be transformed into current source that is connected in parallel with the resistance Rn. So you can use source transformation to go from this voltage source to this current source, or you can go from this current source to a voltage source, so vice versa. Now we know that Rn is an equivalent circuit when all the voltage and current sources are removed, and RTH is also the equivalent circuit when all the voltage and current sources are removed. So Rn and RTH are always equal, so we get the same value whether we use a Thevenin or Norton equivalent circuit. So Rn and RTH are always equal, and VTH and Rn can be related through Ohm's law. So VTH is nothing but IN times Rn. So therefore IN is VTH over Rn. But since Rn and RTH are equal, so this is equal to VTH over RTH. That's IN. So we are using source transformation to go from a Thevenin to Norton, or from Norton to Thevenin. So you can determine one if you have the other equivalent circuits. So this is all about Thevenin and Norton equivalent circuit, and in both cases, our goal is to simplify complex circuits by replacing with one independent source and one resistor. If we have a Thevenin equivalent circuit, those independent voltage source and an equivalent resistor are connected in series. If we have a Northern equivalent circuit, that independent current source and the resistance R, or the equivalent resistance R and are connected in parallel. So in the next video, I'll solve a couple of problems related to Thevenin and Northern equivalent circuits.